Molar conductivities of ions. So first of all, what is the molar conductivity? The molar conductivity is of an electrolyte in solution is represented as equation number 1, which is the ratio of the specific conductivity over the concentration, and the unit of the molar conductivity is Siemens centimeter square per mole. Whereas when the concentration is taken as in moles per decimeter cube, then this equation number 1 is modified as equation number 2, in which we need to multiply with 1000. So the second is what is the specific conductivity. It is the inverse of resistivity, having unit is Siemens per centimeter. And the third category is known as equivalent conductivity, which is actually the molar conductivity over the constant, which is usually the ratio of the molecular mass over equivalent mass. For example, for solution containing the electrolyte have shown in this chemical equation, which is showing the dissociation of the electrolyte solute within the solvent. So here the equivalent conductivity is equal to the ratio of the molar conductivity over these valences. So now come back to the molar conductivity. Here molar conductivity is the conductivity of the solution having all electroactive species which are contributing to the overall molar conductivity of the electrolyte solution. So here molar conductivity is the total conductivity of all the ionic species present within the electrolyte solution. So here let's consider only one electrolyte species, that is species B. For this one, for this kind of ions, they will contribute separately to the overall conductivity of the solution. For this ion B, the molar conductivity will be expressed as the symbol lambda, that is the conductivity of a specific species, and that will be equal to the specific conductivity produced by the ionic species B over its concentration. So here kappa B is the contribution of ion B to the solution's conductivity, and Cb is the molar concentration of the ion B. So here the Cb is the actual concentration of ion B in the solution, whereas C in the total molar conductivity is the electrolyte's stoichiometric concentration. Have described in the previous lecture that the mobility of the ion B expressed in terms of the specific conductivity of the species B was actually valency of this ion and Faraday's constant, where UB is the electric mobility of ion B and the concentration of ion B. So by comparing this equation number 5 and 6, we can write the molar conductivity of ion B in terms of the mobility. So here we get the molar conductivity of ion B in terms of the mobility is equal to its valency into Faraday's constant and the mobility of ion B. So using equation number 7, we can measure the molar conductivity of a specific ion, that is for B we can calculate it from the mobility. Similarly, we can write the equivalent conductivity of ion B as molar conductivity of ion B over its valency, or the amount of the positive charge, that is for example, if we are taking copper 2 plus, then the value of Zb will be 2. So here the molar conductivity is given as equation 7, so we can compare the equivalent conductivity as this one divided by the valency, so it will be equal to the Faraday's constant and into mobility of ion B. For the electrolyte solution containing only species B, the molar conductivity due to ionic species B will be equal to the 1 over C and summation of the number of species B having concentration B into the molar conductivity of the ion B. That is, from here the specific conductivity is equal to the concentration of species B into molar conductivity of the ion B, and comparing this equation with substitution to the value, the equation 5, overall conductivity will be expressed in the summation of equation 5, that will be contributing the involvement of all ionic species B. So this equation number 9 is relating the molar conductivity of the electrolyte to the molar conductivity of the ion or ions. For a strong electrolyte, for example, Mv plus and Xv minus, which is completely dissociated into respective ionic species, the molar conductivity due to these ionic species will be equal to the inverse of total concentration into concentration of the positively charged species and the molar conductivity of this positively charged ions plus concentration of the negatively charged species and molar conductivity of this negatively charged species or ion, that will be equal to the expression given here for this kind of strong electrolyte which have been dissociated to Mz plus and Xz minus. So here the relation have been modified stoichiometrically according to this kind of electrolyte. So here we can see that the concentration term within this bracket can be taken as common and can be cancelled with this concentration. So overall this equation can be again simplified as the molar conductivity due to ionic species given here is that is question number 10, or that is for strong electrolyte which means that there are no ion pairs. So alternatively we can say that all this paired species have been dissociated into these kind of ions. For example, for the case of magnesium chloride, this equation is providing that there are no ion pairs. That is again for strong electrolyte. Now consider an example of a weak acid which is partially dissociated into the ionic species, and for this kind of acid the degree of dissociation is given as alpha. For this kind of weak acid we can rewrite the equation number 10 as the molar conductivities of the positively charged and negatively charged dissociated ionic species with multiplication of the degree of dissociation, and the total molar conductivity is less than the molar conductivity of respective ionic species with a factor of alpha, that is the degree of dissociation. And this equation holds good for the 1:1 weak electrolyte, that is for example given here. Similarly, for infinite dilution, for the weak acids, the dissociation coefficient or the degree of dissociation is not equal to 1 for the weak acids, then the molar conductivity at infinite dilution will not equal to the sum of the molar conductivity of the positively charged species at infinite dilution and the negatively charged species at infinite dilution. In all these terms, the molar conductivity is actually any ionic species like B is contributed by the mobility of ion. So greater the mobility, greater will be the molar conductivity of the particular species. And we have observed previously in the discussions that the mobility of the ions at infinite dilution is higher as compared to the concentrated solutions. Equation 11 gives the molar conductivity for the weak electrolyte, whereas for the strong electrolyte we can write the equation as where the degree of dissociation equal to 1. So here we have V valent and B minus valent anionic species at infinite dilution. Since there is no ionic pairing in the infinite dilution, the mobilities of the ionic species can be calculated from the conductivities that are the molar conductivities of the ionic species at infinite dilutions. So we can use the equation here. The molar conductivity of the species, let's be at infinite dilution, is equal to the valency into Faraday's constant, then its mobility at infinite dilution. So now this mobility, which is also related to another term known as transport number. Transport number of any ionic species, let's be in an electrolyte solution, is defined as the fraction of the current it carries. For example, TB, and this is the transport number for the ionic species B, is almost equal to the current density produced by this species over total current density. So we can call it type of mole fraction. So the transport number for species B is the ratio of the current carried by the species B over the total current density. So here is the current density carried by species B is given as the equation in previous lecture, whereas the total current density is the product of the specific conductivity into electric field strength, or the magnitude of electric field. So on account of these two values, the transport number for species B is written as the valency of species B into Faraday's constant, concentration, drift speed over specific conductivity into field strength. So we can again simplify this equation as in terms of the mobility, that is the ratio of the drift speed over the field strength. So here the transport number for a particular species, for example for species B, is given here. It can be calculated using the mobility and the conductivity measurements. As for the total mole fraction of any solution must be equal, so the transport number for overall solution must be equal to 1. For example, total transport number for all ionic species that are positively charged will be equal to the current density of the positively charged ionic species over the total current density of the positively charged and negatively charged ionic species. So this fraction can be correlated with the mobility and the drift speed of these kind of species. So again we can write the ratio of the drift speed of the positively charged species over the drift speed of the all type of species present in the electrolyte solution. This ratio again will be equal to the mobility of the positively charged species over the mobility of all the ionic species available in the solution. Or they are dissociated in the solution. Similarly, for the negatively charged species, the transport number can be written as the current density contributed by this negatively charged species that have been dissociated from the electrolyte solute. So here we have the total current density of the all ionic species that have been dissociated into the solution. Similarly, we can express the transport number in terms of the drift speed and as well as the mobility. So here one thing is interesting that at infinite dilution the transport number and the molar conductivities are related. For example, for a strong electrolyte, again taking an example of the Mv plus and X V minus type of electrolyte, the transport number for the positively charged species is written as the current density contributed by this species over total current density, that will be equal to the specific conductivity contributed by this species into the electric field strength over total conductivity into electric field strength, that is again equal to the specific conductivity of the ion over the total conductivity of the solution. And again this ratio is equal to the molar conductivity due to this ion into concentration over total conductivity into concentration. And at the infinite dilution there isn't any ion pairing, or these species have been dissociated. For this case the C plus will be equal to for this valency. So for the strong electrolyte, the transport number for the positively charged species can be calculated in terms of the infinite dilution. That is, the transport number for the infinite dilution is equal to the molar conductivity at infinite dilution into the stoichiometric constant over the total molar conductivity of the solution. So here we have the value of the total molar conductivity. So here we can see that how we can calculate the transport numbers at infinite dilution, as well as in terms of the molar conductivity. Here these are the transport numbers in terms of the molar conductivities, whereas these are the transport numbers at infinite dilution, so they are expressed in terms of the equivalent conductivity. So today's discussion was based on the solutions that are electrolyte solutions, but all these equations are applicable for the dilute solutions, and as well as we have derived all the expressions for infinite dilutions that are termed as equivalent conductivity or equivalent transport number, or the terminal speed, and the mobility of ionic species at infinite dilutions. So for the concentrated solution, we have already discussed the Onsager force equation in previous lectures, which are describing the molar conductivity of the concentrated solution while incorporating some constants which are relevant to the viscosity. So we already have discussed the contribution of the ionic species for a concentrated solution using the Onsager force equation. That was the theoretical equation based on the experimental determinations or the real experimental data analysis.